Good afternoon, colleagues. Let me present some study results on stress analysis in a spherical pressure vessel with multiple defects. To begin with, I would like to say a few words about the relevance of the problem. Pressure vessels are carefully fabricated, enclosed containers designed for the purpose of holding either gases or liquids at a significantly different pressure than the surrounding air pressure. These vessels have a variety of applications in the industrial market and the private sector. Some examples of pressure vessels are distillation towers, hydraulic reservoirs, containers for fluids or liquefied gases, and many other types used in mining operations, oil refineries, and petrochemical plants. It is thought that the market volume of pressure vessels used in many different industries will increase with new investments made in the coming years. Hypothetically, pressure vessels can take many different shapes. However, generally preferred geometries are spherical, conical, and cylindrical. Sphere is an ideal shape to hold internal pressure. This type of vessel is preferred for storage of high-pressure fluids and liquefied gases. An advantage of spherical storage vessels is that they have a smaller surface area per unit volume than any other shape of vessel. This means that the quantity of heat transferred from warmer surroundings to the liquid in the sphere will be less than that for cylindrical or rectangular storage vessels. Loading and severe operating conditions often cause various defects on the surface of structural elements. As the weighted part of the pressure vessels produced is manufactured with metal materials, corrosion may lead to general wear or initiate the appearance of local damaged areas. Once appeared, surface defects act as stress concentrators, causing high local stresses and resulting in acceleration of destruction of structural elements. To assess the strength and reliability of the structure, it is necessary to carefully analyze the stress concentration near defects. Many authors investigated the effect of surface multiple defects on strength, fatigue life, and buckling behavior of structures experimentally and numerically. Among the latest works, a number of studies on cracks in vessels of various shapes can be noted. A number of recent studies is also devoted to the influence of pitting corrosion. Some authors investigated the effect of interacting defects on the behavior of the structures. The main aim of this paper is to investigate the impact of defects clustering phenomenon on the high cycle fatigue limit, a cylindrical volume with spherically longitudinally aligned defects, where the defects are parallel to the cyclic tension load axis, and also with circumferentially aligned defects is considered. Numerical study based on finite element analysis showed that the defect configuration and the defect spacing significantly impact fatigue strength. In our study, we consider a spherical vessel under fixed internal pressure with multiple defects on its outer surface. The defects are assumed to have a form of hemispherical notches of the same size. We consider hemispherical cavities with a depth equal to half of its radius. Random arrangement of defects along the equator of the sphere is modeled. Different numbers of notches are considered. Two cases are investigated: linearly elastic model and also elastic plastic model with linear strengthening. It is required to analyze stress distribution in the vicinity of notches, depending on geometric parameters of the problem, and investigate the effect of the distance between neighboring defects on the growth of stresses in the vessel for different numbers of defects in the framework of linear and bilinear models. To perform a finite element analysis, we built an array of 3D models of geometries of notched spheres. Iron Python scripts were created to automate the modeling of random defect patterns. A series of finite element calculations were carried out by ANSYS Workbench package. Properties of materials under consideration are shown in the tables. First, we consider a linear elastic model. For every number of n, 5 geometries with random distribution of defects along the equator of the sphere were built. The maximum relative stress observed in the vicinity of defects for various numbers of these defects is shown in the figure. Here the points of different colors show results for 5 different geometries for each number of defects. Note that overlaps between neighboring notches took place for all considered numbers of defects. It is seen from this figure that an interaction between the stress fields near neighboring notches is observed regardless of n, resulting in the non-monotonous change of the maximum principal stress as n grows. We compare these results with the results obtained for the uniform distribution of defects along the equator of the sphere. The interaction between the stress fields around neighboring notches for the random pattern leads to stress concentrations greater than in the shell with evenly distributed notches for the same number of defects. Though the maximum stress values for evenly and randomly distributed notches are approximately the same, namely the difference between the maximum values is 8.6%. However, for evenly spaced defects, this maximum is observed for a relatively small range of varying number of defects, while for the random distribution, this maximum is observed for a larger range of numbers. It was found that for all the defects where the maximum stress is observed, the distance to the nearest notches is close to the average one. Average distances between the defects with maximum stress for different numbers of n are demonstrated in the figure. The red points mark the distance values averaged over each value of n. The black line shows the global average distance between defects with the maximum stress for all geometries built. This average distance approximately corresponds to cases in which adjacent notches either slightly overlap or there is a small distance between them, resulting in a sharp edge. These observations are consistent with the studies of other authors, for example, some articles from the review. At the same time, the maximum stress is not always observed when the distance to adjacent defects is close to average one. That is, there is no reliable causation between the distances between notches and the stress increase. Thus, we can see that the distance between the nearest defects is not the only factor affecting the stress concentration. The mutual arrangement of all the defects on the surface must be taken into account. It could be concluded that the stresses depend on the entire distribution of notches over the surface. In most cases, maximum stresses generally occur in the edge between adjacent defects. In reality, sharp edges between corrosive pits often tend to be smoothed, so we build smoothed geometries to consider these geometry variation. The maximum relative stress for various numbers of n occurred in original and smoothed geometries is demonstrated in the figure. For a large number of defects, maximum stresses in smoothed geometries are about 20% lower than those in the original geometries. The following figure shows maximum relative principal stress and relative von Mises stress dependent on the distance between defects in the range containing the average value observed in geometries with only 2 notches. In this case, it is also seen that as the defects get closer, the stresses change non-monotonically. Stress increase with decreasing distance is observed only up to a certain critical value of the distance. After reaching this value, the stresses begin to decrease. Similar behavior was observed for n notches. A bilinear model was used to calculate stresses above the yield point. The strain hardening portion of the stress-strain curve was modeled in ANSYS Mechanical using bilinear hardening model. Bilinear hardening rule assumes a linear strain hardening portion and is defined using a tangent stiffness. The same analysis was implemented in the framework of bilinear plasticity hardening model for large internal pressure, when the stresses in the vessels exceeded the yield limit. As one can see, the dependencies of the maximum stress on number n are qualitatively the same as in the case of linearly elastic problem. However, the stress concentration in the elastic plastic model is lower than in the case of the pure elastic model. To sum up, we can conclude that the maximum stresses for evenly and randomly distributed notches of considered geometry differ by approximately 8.6%. For evenly spaced defects, the maximum stress is observed for a relatively small range of the number of defects, while for the random distribution it is observed for a noticeably larger range of the number of defects. In most cases, the maximum stress is observed at the sharp edges between notches that slightly overlap or almost touch each other. However, these can be affected by the arrangement of other defects around the considered couple. The dependencies of the maximum stress on the number of defects are qualitatively the same in the cases of linearly elastic and elastic plastic problems. However, the stress concentration in the elastic plastic model is lower than in the case of the pure elastic model. Thank you very much for your attention.